Okay, guys, topic 3, we're going to talk about now beta radiation, and also sometimes gamma radiation will follow beta, so we'll be talking about gamma again. Okay, so we're going to look at both beta minus and beta plus nuclear decay. Okay, and we're also going to look at one other process called electron capture, where you don't have anything coming out of the nucleus, but it is a way for a nucleus to achieve stability, and it's related to beta plus decay, so we'll also look at that, but I didn't list it here since nothing's coming out of the nucleus. Okay, so let's go ahead to beta decay, and we'll do beta minus first. So the process is the nucleus, to try to achieve stability, is going to eliminate a neutron in its nucleus. Now, it doesn't just spit out the neutron. Okay, no, that doesn't happen at all. This is going to occur when you have a nucleus, and this is usually not going to be the really big guys. The big guys will spit out alpha particles, but these are going to be sort of medium-sized guys or small guys that have too many neutrons, and so they're a little bit unstable, and they're going to try to get rid of one neutron. What happens inside the nucleus is amazing. Inside the nucleus, you'll actually have a neutron decaying into a proton and an electron and this guy. This is a new, there, can't quite see it, but there should be a bar completely over that new. Okay, so the electron is what we call the beta minus. Again, historically, people didn't realize that these beta particles, these beta minus particles, were in fact electrons. We now know that. This new with the bar over it, this is a new type of particle that we haven't talked about before. It's called an antineutrino. You may have heard of neutrinos and antineutrinos maybe in the science news. But neutrinos and their antimatter counterparts, antineutrinos, are very, very weird particles. For a long time, people thought that they were just photons. But we now know that they do have a very tiny, tiny mass. Smaller, much smaller than that of the electron. So they are mass particles. However, they do not carry a charge. And because their mass is so small, they really don't interact much with regular old matter. So they're very hard to detect. For a while, people didn't even realize that antineutrinos were following this beta minus decay. It took really careful measurements to realize that there was something not right in the mass conservation going on. Okay, so the antineutrinos in the beta minus decay, they're going to come flying out of the nucleus, and they will take some of the energy release in the decay, but they're very hard to detect, extremely hard to detect. Only a few places can detect them. A few labs that have special detectors with special experiments set up. Okay, so we have to remember that there's an antineutrino when we write the decay equation. Okay, so again, this is amazing, right? In fact, isolated neutrons, if you just have free neutrons, they are unstable. They will actually decay. In fact, let me see something. I think in our isotope data table, oops, sorry. If we go to the isotope data, yeah, right here. See right here where they have neutron, right? An isolated neutron is actually radioactive. See, it decays via beta minus decay. And we'll talk more about this half-life in the next video, but it's around 11 minutes. So that's relatively short half-life. That means that if you had a population of neutrons, after about 11 minutes, half of them would have decayed. Okay, so now in a bound nucleus, right, certain neutrons are stable, right? So if you have a stable nucleus, those neutrons are very happy and they're not going to decay. But if you get one that has too many neutrons, you're going to have beta minus decay. Okay, let's get back to the presentation then. Okay, so that's the process. How do you write the decay equation? Okay, the key is you're going to have the parent over here with atomic number Z. The key is to write these two guys. Write the beta minus particle like this. Put a -1 downstairs and a 0 upstairs. That will give you the right daughter atomic number and mass number. And you also have to remember to write the antineutrino. Again, that's a nu, and that bar should be extending all the way over. The bar over the nu means it's an antineutrino. Okay, so the key again is to write this combination, in particular the beta with the -1 downstairs and the 0 up here, because that's going to force you to write the atomic number of the daughter as the parent number z plus 1. Okay, because we have to get, right, z on the right side also. And that's going to force you, if you notice, see, in the process, a neutron's going into a proton. The proton stays in the nucleus, so that means the atomic number's got to go up by 1. The mass number, however, does not change. And having a 0 here gives you the same mass number in your daughter as the parent. The mass number doesn't change because you're just swapping a neutron, right? I'm sorry, a neutron for a proton. So the number of nucleons stays the same. All right, so the radiation, again, is the electron and the antineutrino. To find the energy released, again, we're going to do a mass deficit multiplied by c squared to get the so-called Q. Here, though, all we're going to have to do is take the parent mass minus the daughter mass. Now, I'm neglecting the mass of the antineutrino. It's negligible. So it might look like, though, I should subtract off the mass of an electron, right? And you don't see that in this equation. Theoretically, that's right. However, because we're using atomic masses, that's going to be automatically done for me. Remember, the table that we use is has the mass of atoms, not the nuclei. So when I take a neutral parent atom and subtract off a neutral daughter atom mass, I'm already taking off an extra electron, because the daughter neutral atom is going to have one more electron than the parent. So just go mass of parent minus mass of daughter. You've got the mass deficit. Okay, it is possible that gamma decay occurs after a beta minus. So if that's the case, similar to what we did with the alpha, we're just going to write the beta minus decay, but put a little asterisk on the daughter, and then rewrite that with the excited daughter going to the unexcited daughter plus a gamma. Let's do an example. Let's write the beta decay equation for carbon-14 and find the energy release in the decay. Okay, so to write the beta decay equation, I'm going to go to my trusty table. I know carbon is atomic number 6. I find carbon-14, and if you come over here, you'll see just beta minus. So this does not have a gamma decay following the beta minus. This is a pure beta emitter, as we would say. So all I have to do then, when I go to write my equation, right, is I have my parent, carbon-14, atomic number 6. I write down the beta, right, like this, -1 downstairs, 0 up there, plus antineutrino. And then I say, okay, I know I've got to get a 6 over here on the bottom. I've got a -1 here, so that's got to be 7. As soon as I know atomic number 7, I know that's nitrogen. You can go back to the table and verify that. The mass number of the nitrogen is going to be 14, same as the parent. So that's going to be nitrogen 14. Okay, there it is. Now, to find the energy released, I first find the mass deficit. I'm going to take the parent mass minus the daughter mass. So if I go back to my table, let me go back to my table. Just make sure you see where I'm getting these numbers. I'm going to take carbon-14 mass, which is right here, 14.003242. I need nitrogen-14 mass to subtract from that, 14.003074. Notice that the carbon-14 mass is greater than the nitrogen-14 mass. Not by much, but it is. So that's good. That makes sense. Oh, also, while we're here, just notice, see the nitrogen-14? See, I have 99.63 here. That means that's not radioactive. That's stable. And in fact, almost all of the nitrogen, right, is on the Earth is going to be nitrogen-14, 99.63%. Okay, let me go back to our PowerPoint, and we'll finish this calculation. So I take the difference of the masses. I get 0.000168U. I multiply by my handy conversion factor and c squared. I end up with 0.1565 MeV, and that is the kinetic energy of the beta minus particle and the energy of the antineutrino. I didn't say that well. What I mean is this is shared between the beta minus and the antineutrino. How it's shared, I don't know. There are going to be actual values for those in a carbon-14. There might be a couple different ways it gets split, but I'd have to look up those details. Don't worry about that. But there are going to be one or two ways that that's always split for a particular isotope. Okay, let's do another one, which is a beta-gamma decay. So let's look at cobalt-60. So if I go to cobalt-60 in my table, okay, and again, you can look up the atomic number for cobalt. Just type in cobalt in a search bar. But I'll remember that cobalt is 27. Cobalt-60 sometimes used in nuclear procedures. So if I find cobalt-60, see right here, I have beta minus, comma, gamma. So I know that that is a beta minus followed by a gamma. All right. So when I go to write my decay equations, what I need to do is I'll first write down the beta minus decay. And again, whoops, sorry, wrong one. I immediately write down beta minus 1, 0 plus my antineutrino. Since this is 27, I know this has to be 28. If you look up 28 in the table, you're going to find nickel. The mass number is the same as the cobalt isotope 60. Because I have beta minus decay following, I put a little asterisk here because this is an excited nuclear state, in an excited nuclear state. And then I just rewrite my excited daughter going to the unexcited daughter plus gamma. Okay? To find the energy released, I still take parent minus daughter mass. There it is right there. If you look up the masses in the table, I multiply by c squared and my conversion factor. I get 2.8234 MeV. Now, that's going to be shared between three things now, right? The beta minus particle, the antineutrino, and the gamma ray. And how that gets split, again, it's going to be one or two ways, maybe even a couple different ways for a given isotope. But again, don't worry about that. We're not going to worry about how that gets split. But you should be able to do a Q calculation and realize that that is going to be split among those three particles. Okay, beta plus decay. This is going to occur only for neutron deficient nuclei. So these are going to be nuclei that don't have enough neutrons. Okay, they're neutron deficient. And what happens here, again, it's fascinating. A proton in that nucleus will change into a neutron, a positron, and a neutrino. So the beta plus, that's a positron, an anti-electron, and then a neutrino. See, I don't have a bar over the nu, so that's a neutrino. Now, a proton will not do this on its own. It does have to get some energy from the nucleus. Okay, so protons by themselves are not radioactive. But an unstable nucleus that doesn't have enough neutrons, it will take a proton plus some of its energy, nuclear energy, and do this process. So now when we write the decay equation, it's similar to beta minus. The change is we're going to write the beta particle with a +1 downstairs. And then we have to remember to write the nu. Not an anti-neutrino, but a neutrino. No bar above the nu. But by making that beta have a +1 subscript, that forces the daughter to have one less proton than the parent. And having a 0 upstairs gives us the same mass number. That's what we need, because here a proton, right, is going to be replaced by a neutron. What comes flying out of the nucleus is the beta plus and the neutrino. Now, just like with beta minus, you have a mass deficit calculation. Here, though, what you have to do is, because we're using atomic masses, you would take the parent minus the daughter, but you're going to have to take off 2 electron masses. One for the beta plus, but another one because the parent has an extra electron in it. Okay? But you know what? Between you and me, I'm not going to have you guys calculate the Q for beta plus. It's redundant. So just know how to write the decay equation. You can have gamma following a beta plus. So just like we have been doing for the alpha and the beta minus, you would write the original beta plus decay, with an asterisk on the daughter, and then rewrite it with the starred daughter going to the unstarred daughter plus the gamma. Okay, so for beta plus, don't worry about finding the mass deficit in the Q, but you should be able to write down the decay equation. So for instance, can you write down the beta decay equation for nitrogen 13? And let me just show you guys, right? If you go to the table and I look up nitrogen, that's atomic number 7, nitrogen 13, see, there's a beta plus. Okay, so no gamma, so this is just a pure beta plus. So if I want to write down that decay equation, I say, okay, I write down, oops, sorry, you guys can't quite see that. So let me scroll up and make this a little bit bigger. I put that a little bit too far. Okay, I think you can see that. So I write down the beta with a +1 downstairs, a 0 upstairs, plus the nu. The nitrogen has 7, so I have to have 6 protons in my daughter. As soon as I know that's 6, I know that's carbon, and then the mass number is the same as the nitrogen. And look at that. I put a 14 right there. That is incorrect. That should be a 13. I'm so sorry, but I am not going to re-record this video, so that should be a 13 right there, guys. Okay? You got that? In fact, let me see if I can do that right now. I probably can't do it with the pressure. 13. Okay. So that should be put right there. That's a 13. Got it? Okay, sorry about that. All right, one last thing. I'll fix that. I'll fix it so when you grab it, the PowerPoint, it'll be corrected. But the video, this is what you're getting for the video because I'm not going to re-record this. Okay. All right, let's go to, real quickly, electron capture. This is another process where a neutron deficient nucleus can gain a neutron. I'm sorry, I got distracted. So this is so cool. What happens here is that proton will actually recombine with an electron from the atom. So an electron that's orbiting the nucleus will actually go into the nucleus. It'll recombine with a proton, or I should say combine with a proton to form a neutron and a neutrino. So there is a neutrino coming out. So I first said there's nothing coming out of the nucleus. There actually is. There's a neutrino. But we don't really count that as nuclear radiation because neutrinos and antineutrinos don't really interact much with matter. So this is another process, and it sometimes competes with beta plus decay. You have certain isotopes that'll do either beta plus or electron capture. But the nucleus will actually combine with an electron from the inner shell of the atom. One of those electrons will come inside the nucleus. A proton and that electron will form a neutron and a neutrino. So it's a neat process. So just be aware of it. But that's it. All right, I'm going to stop right now. Bye-bye.